Hi all, my name is José Luis Salazar and I'm going to present our work Short Message Multichannel Broadcast Encryption. This work was made by José Luis Salazar, José Saldaña, Julián Fernández Navajas, José Ruiz Mas, Guillermo Zora Guillén, in the Zenit Researcher Group from the University of Zaragoza, Spain. We are going to use this index to explain our work. We shall show on an example that serves as a justification for carrying out the work and then formally state the work to be done. We will review a little background on the problem raised. Then we will describe the two possible approaches that will help us to analyze the efficiency of our implementation. And we shall detail our chosen approach. Finally, we will analyze our proposal comparing the bandwidth and channel utilization efficiency of the two approaches. We shall end presenting the conclusions. Nowadays, the use of the short messages through the internet is proliferating quickly. Voice over IP, Instagram, Twitter, WhatsApp. When access is done through a wireline, there are usually no connectivity or efficiency problems, unless the conditions of this network are very constrained. When access is through a cellular network, we will subject to the network's known restrictions, but once access is obtained, the condition will not change much. On the other hand, when the access is by Wi-Fi, we have a deep problem since the connection to the access point is not always guaranteed and it has to complete to send its packet with the rest of the stations that try to connect to the same access point. In addition, the security in this type of Wi-Fi link overloads the bandwidth a little, which then has a strong impact on the efficiency of the utilization of the channel. For the increased efficiency in communications, our research team has been supporting for several years on aggregation of packets. In these two frames, we can see how efficiency decreases when the data group that is included in each packet is small. In the first frame, we realize that if the payload is less than 40 bytes, the efficiency of the channel utilization is less than 50%. The second frame is even worse. The data is included in a group of information whose size is bottom bounded twice. In one of those bounds, it is the only field with a variable length, and then the payload may be padded. MSDU aggregation relies on the fact that most mobile access points and most mobile client protocol stacks use Ethernet as their native frame format. It collects Ethernet frames to be transmitted to one or multiple destinations and wraps them in a single standard frame. This is efficient because Ethernet headers are much shorter than Wi-Fi headers. An MSDU unit contains only MSDUs whose destination address and sender address parameter values map to the same receiver address and transmitter address values. Ergo, all the MSDUs are intended to be received by a single receiver, but its address could be a multicast address. There exists also an MAPDU MAC protocol data unit aggregation. This mechanism allows each of the aggregated data frames to be individually acknowledged or transmitted if affected by an error. We then return to the proposed Wi-Fi scenario. If we want to use frame aggregation, then we will have to provide it with security. And that's the question, how to do it efficiently? Background, really not much. In the 80s, pay TV broadcasting methods became fashionable. The challenge was to send the coded signal so that the receivers who had paid could deploy the contents. For this, information frames were used with the identifiers of the users updated at the time of the payment, some random headers, and with them the key was built with which they create the contents, each one his. In the classic model, use is used to identify the user. In our proposal, it is not needed to identify the users because the identities are joined in a group address. Now, header is a random seed. Cs are the encrypted messages with header that are just multiplexed by means of the Chinese reminder theorem. Here are the simplified encryption and decryption formulae. To know the details and the security proof of the algorithms can be consulted in the conference proceedings book. We had two ways for implementing security. This way can be easily implemented with the last version of Wi-Fi standard. But this one has to embed the new algorithms in the implementation. We can compare the option. Given the needs of communication of small packets in terms of security and efficiency, our main objective is to find a balance between efficiency and security that are usually becoming antagonistic issues. Our proposal is more efficient for Wi-Fi standard, provided that user's packet size has an upper bound. The savings will be optimal if the key size is only slightly higher than the packet size. Thus, in services that send packets of the same size, for example, voice over IP, an optimal key can easily be selected. Here we represent the delimiter of the areas for improvement of our proposal. It should be noted that efficiency is improved in the space above the curve. It can be observed that the minimum average size grows linearly with the level of security. When we analyze a wireless link, we must take into account not only the bandwidth in terms of bytes sent, but it is also necessary to consider the mechanism for medium access. If we have to wait for the medium to be free, then we have to send a lot of packets through it. We will accumulate a lot of waiting time. Hence, sending a smaller number of frames, a single frame for a number of users instead of a number of unique ones, can improve the spectrum utilization. Here, we compare our proposal of using secure multicast AMSDU versus the use of secure AMPDUs in terms of efficiency in the downlink. The size of each of the aggregated packets is determined by the size of the key. Three different key sizes, 1024, 2048, and 4096 bits are used. We can see how the general efficiency grows when the number of aggregated packets or the bit length average packet size is increased. It can be observed that in general our proposal based on multicast AMPDUs outperforms the one based on an MAPDUs. Only the biggest key 8% a lower performance if the number of users is below 13. We have designed an efficient broadcast encryption system for traffic of small packets. We have used the Chinese reminder theorem to multiplex the encrypted message and made unique the random source for encryption. The results improve the bandwidth saving and the airtime connection when compared to encryption of a multiple unicast packets, granted that the average packet size requirements are satisfied. Thanks for your attention and be safe.